Okay, let's get going. So we have the midterm on Wednesday. And then today, what I wanted to do was to talk a little bit more, just a couple more slides out of this simple filter stuff, and then do some review. I put together this new overview slide, which I felt was had a sudden vision of how everything links together. We'll see how that works out, and then also I can either answer questions or we can look at the past midterms as well, or anything you want to do for the amount of time we've got. Sound okay? All right, let's just pick up where we were last time then, just for a couple of seconds here. And so I've responded to email from a few people about exactly which topics are covered in the midterm. And I have difficulty answering that, because if I said, well, we're not covering this material on simple filters, that wouldn't be true, because there's no way we can not cover it, because it's just an application of the stuff we've been doing before. But the idea is that the midterm is on all the stuff up through the Z transform. I can't find the thing. On the time domain systems and Fourier transform and the Z transform. Basically, that's the theoretical core of the class, and that's what the test is about. But the stuff we're covering right now is just sort of, some consequences, some applications of that. So I'm not specifically... I sort of understand why the question comes up, because it's like, well, which parts do I need to look at of the material we've got when I'm revising? And you should look up to what we covered, I guess, last lecture. But if you only looked up to the end of the previous slide pack, you'd still know everything, right? But this can actually help you understand a little better, because it's showing some of the consequences. I don't feel like there's any kind of new knowledge here. It's just exploring some of the implementations or, what happens, some different kinds of filters. Okay, so at the end of the last lecture, we were looking at this bandpass filter by having a system with two poles, which means we need two parameters to specify them, the real and imaginary part, or the angle and the radius, however you like to control them. With two poles, we can vary both a center frequency and a bandwidth for a bandpass filter. And then we can make it a slightly nicer bandpass filter by adding two zeros at the both extremes of our frequency axis. And then if we have, what we typically want to do is we want to build a bandpass filter with a particular center frequency and a particular bandwidth, and we can control that with two different parameters. For this particular structure, we have these design parameters alpha and beta. Once we know alpha and beta, we can get the parameters of the difference equation, or the Z transform, which leads to the difference equation straightforwardly. But alpha and beta independently control the center frequency, beta controls the center frequency, and alpha controls the bandwidth here through these simple design equations. And we did a quick example just to show you that if we have a specific specification like this, we want a center frequency with a particular peak and a particular bandwidth in terms of, these are now actual units. They're in normalized frequency because it's radians per sample, but they're actual specific frequencies. Then we can figure out the actual filter, and here we've got filter design, which we can basically turn these numbers into the arguments to a filter command in MATLAB and build the filter that will do that bandwidth. And we do that bandpass operation. We looked at the frequency response, the frec-z of it in MATLAB, and yes, it did have a peak of the appropriate bandwidth. What I didn't do was actually use that filter, but if we'd actually taken a piece of sound and run it through that filter, we would have heard this narrow bandpass response. And of course, you can put that into any other implementation, like the PD, real-time audio stuff we looked at the beginning of the semester. Just to sort of get to the end of this section, one other kind of filter that we might sometimes want to use is a band stop filter, which is sort of the converse of the band pass filter. So at most frequencies it has a gain of 1, but for some specific range of frequencies it has a much lower gain. We have a center frequency where we can actually achieve a gain of 0, but it's just one frequency. And then we have some bandwidth B where the gain is less than 3 dB below the peak. So again, we've got a 3 dB bandwidth, but now it's the bandwidth where the gain is below that much. The way we do this is a little interesting. It's this pole 0 pair that we've looked at a few times. We have a 0 on the frequency axis on the unit circle to achieve this frequency at which we have 0 gain. But then we have a pole very close behind it. And for a very narrow bandpass filter, the narrower the bandpass filter, the closer the pole gets to the unit circle. And one way of thinking about or interpreting what's happening is, it's this pole 0 cancellation. So if they're very close together, for a lot of points on the unit circle, they're essentially cancelling each other out because the two vectors going to each of them are about the same length. So when you take their ratio, you get 1. But as you get very close to these frequencies, the 0 dominates. So you get this situation where you have a notch in there because suddenly the vector to the 0 is much shorter than the vector to the pole. And so the length of the 0 vector divided by the length of the pole vector becomes a small number, which gives us this notch. It turns out that the pole locations are the same as we had with the band pass filter. We've got the same beta and alpha and the same design equations. I guess not the same design equations. We've got the same center frequency from beta, but I guess this is a different alpha. And then we also have the 0 is now different because instead of having these zeros out here, we've moved them around here, but they're just controlled by the center frequency beta because they're just on the unit circle. And so it's kind of interesting, like if we take these two zeros and move them here, we get a band pass filter with a peak at this frequency. When we move them to here, we get a band stop frequency with a notch, band stop filter with a notch at that frequency. But the pole is sort of, in the band pass filter, the pole is actually providing the boost at those frequencies. In the band stop filter, the pole is sort of compensating for the broad notch that the 0 alone would give, and by boosting it around, by boosting those frequencies, but not as much as the notch, we make the band stop region narrower, so we can control the bandwidth of the band stop filter. So one other thing we can do to generate different filters. Often we're interested in in having a sharp filter, having a filter where for some range of frequencies it's passing the energy unmodified. For another range of frequencies it's almost completely removing the energy, and maybe we want to make the transition region between those two as narrow as possible. So the sharper the filter is, the more rapidly it changes from passing energy to stopping energy. One way of increasing the sharpness of a filter is simply to repeat it. So if we have a single high-pass filter like this, which is basically our simple 2-point FIR high-pass filter. We've got some 3 dB frequency here, some bandwidth. If we just take this response and then add another one and maybe another one, these frequencies up here where the gain is 1, well, they'll be modified by, they'll be scaled by 1 when they go through this one, 1 when they go through this one, 1 when they go, they'll still be, their gain will still be 1 at the end. But these frequencies down here, where the gain is some other number like h, where h is smaller than 1, they'll be h times smaller here. Then by this point, they'll be h times smaller. And by this point, they'll be h cubed times smaller, etc. So you can end up taking a filter like this, and because it's got a maximum of 1 here, you're raising it to higher powers. the point at 1 still stays 1, but everything below that gets squashed down because it's being raised to some number less than 1 to a higher power. And so you end up with a sharper filter like this. If you think about what's happening, what the roots of the system are, if this is a system with a single zero, which is what our 2-point high-pass filter was, then we just get this zero from each of these occasions. We get 3 coincident zeros, right, which I've drawn here as concentric zeros on the poles on the z-plane, which gives us this particular filter structure. There are many ways we could get so now we have a filter with a new 3 dB bandwidth, a high-pass filter with a new cutoff frequency. There are several ways to get that. This is only one, and it's not the best one. We haven't defined what we mean by best, but probably by any metric you can come up with, you can get a better filter for the same cost. But it's maybe the easiest one to design. So the result of repeating a system, the cost of a system, most often we measure the cost of a system by a number of delay elements it involves. And each of these simple 2-point FIR filters involves a single delay element, so they're first-order systems. But when we have 3 of them, suddenly we've got 3 delay elements. We've got a third-order system. For an FIR filter, that the order is the same as the length of the impulse response. This is an all-zero filter. There are no poles, so it has a finite impulse response. This is the impulse response of one instance of that high-pass filter, right? It was this sort of discrete differentiator. It sort of takes delays and then subtracts it out. If we have 2 of these, it's this convolved with itself. So it's this times a half minus a half of this delayed by 1. So it's this and then this thing flipped over and added over. You get this, right? A quarter minus a half, a quarter. And then if you have it 3 times, it's this times a half minus a half of itself delayed by 1, which gives you this, an eighth minus 3/8 plus 3/8 minus an eighth, 0. Right? But what we see is every time we add another one of these, we increase the length of this filter because we're increasing the order of the overall system by the order of this, which is 1 point. So we increase the length of the impulse response by 1 point. So now we've got some kind of third-order FIR high-pass filter. But all third-order filters, even all third-order FIR filters, are defined by 3 zeros on the pole zero plane, right? That's if we take this, we can calculate its Z-transform, we can factor it. We'd find that it had 3 zeros at 1, at omega equals 0. But in general, we can move those zeros around. We still get a third-order FIR system. And for some of those systems, they'll be high-pass. And in general, if we don't constrain the zeros to be coincident, we can get better properties in other respects. So it's not the best way to build a filter. But if you've just got a filter and you want to have a slightly sharper response, then you can always just use it again. And so that's the, run your signal back through the filter again. So that's the attraction of this kind of approach. Here's the response of that on a dB scale, on a log-log scale. That basically, if this is the response of the system, of some system, used once, then if I apply that same thing twice, I'm multiplying every point in the frequency response being multiplied by itself, it's being raised to the power of 2. On a log scale, that just means multiplying it by 2. So this red line, which is the result of using this particular second-order filter twice, is just this thing scaled by a factor of 2 on a log scale. And so with this kind of filter, you can see there's this nice terminal slope, in this case 6 dB per octave, and so the fourth-order system is 12 dB per octave, as you'd hope for. In terms of a design procedure, it's not the most cleanest to use, because normally if we're trying to make a 12 dB per octave filter, I probably want to keep my cutoff frequency the same. which would mean my 3 dB point. But here you see the 3 dB point actually moves back in, because now the frequency that, for the red line, the frequency where the gain is minus 3 dB is the frequency that the gain was minus 1.5 dB on the first filter. So if I actually wanted to get a 12 dB per octave filter with the same cutoff frequency, I'd have to start with a different initial filter, a filter that had a 1.5 dB at this frequency. And then if I'm going to have to design a new filter, I might as well do some other procedure rather than just cascading to second order filters in this case. But this, this behavior here of the terminal slope being 3 times the order is a common thing, and you've probably come across that in analog systems. Okay, so this is this new slide that I put together this here, where I'm trying to put everything together. Okay, so before we talk about this, it looks messy, but that's because I was trying to get everything on one slide. So that's sort of any questions about the simple filter stuff before we start? Now we're sort of moving into revision, discussion, preparation. Okay, so so this is kind of the summary of all the material we've done so far, and I see that there are kind of 4 main representations that we've dealt with. And we're always talking about systems. We're always talking about things that, in this case, we're talking about things that modify signals. And there are 4 ways that we can talk about them. We can talk about them in terms of the time domain and their impulse response, right? So we can actually take the system, we can put an impulse into it, we can measure its impulse response, and if we know the impulse response h of n, then we can generate the output of the system by using convolution, right? So this is one of the pictures of how to interpret convolution. The convolution is a set of delayed versions of the input scaled by different points of the impulse response. And that was kind of, convolution is, not necessarily the most natural thing to do with a signal, but it's what linear systems do. And so it's the sort of the bedrock of what we're talking about, because we're talking about this is the operation we can do, which turns out to be interesting. Staying in the time domain, we can also represent a system by its difference equations, linear constant coefficient difference equation, which is, here it is in its kind of causal form, where we're saying y of n, the output, is the sum of past current and past versions of the input scaled by some constant coefficients, minus the sum of past versions of the output scaled by some constant coefficients. This minus is in here, so when we take it over to the other side, it becomes plus. So that just gives us the d's and the p's that we saw in the general form. But this is just a general form of a system, and of course this reads directly as a block diagram. A block diagram like this has x, current and previous versions of x, the scaling coefficients summed up, and then we have the output y, and then these delays on here give us previous versions of the output. The minus d's give us these terms being summed to give us the current output. And so this is, although the difference equation in its most general form is sort of this abstract mathematical description, when we rearrange it like this, it's absolutely isomorphic to an implementation, to something we could actually build. I mean, I don't know quite why we would consider this to be a more direct expression, because actually what we end up, when we actually implemented this, in many cases we would write something that amounted to this as a statement in some programming language, right, in MATLAB or whatever. And this sort of is this fiction of something where we actually build things with hardware and we put pieces down. But this is still, for me, a more intuitive way of thinking about it, imagining building that hardware that had these actual delays that were delaying signals and scaling and multiplying them. In theory, we could build this out of analog electronics, although, a one-step delay is kind of a nasty thing to have to build in analog. So that's our 2 time domain representations, and we've got a mapping between these two. Well, we can go from the linear constant coefficient difference equation to the impulse response by doing our LCCDE solution. We have the complementary solution and the particular solution, and it's made up of when we worked out what this was, it turns out to be made up of these lambda to the n terms, these exponential terms where the lambdas are solutions of the complementary function, but we have to find the actual alphas, the scales of each of those modes, those natural modes, by inspecting the initial conditions. And then also we've got some output corresponding to the scale version of the input. Basically, the lambda 0 here is if we had a single exponential as the input or a sinusoid, then it would be scaled by some amount. So that was how we can recover the impulse response from a difference equation. Going from an impulse response to a difference equation is actually a little bit tricky. If the impulse response is finite, like this one, then it just consists of the coefficients, these PJ coefficients, right? Because it's just this part of the LCCDE. But if it's a system with poles, then the impulse response is infinite, and it's not clear how you represent that. If you represent it like something like this, as a set of particular lambdas, then you can sort of do it backwards by inspection. But that's why I've drawn this as a light gray arrow, because it's kind of a tricky thing to do. Basically, you have to do it by guessing the answer and seeing that it matches. Okay. The big idea in signal processing is that we can think about these things in the transform domain, in the Fourier domain. And so that brings us over to this column. And that we started off by talking about the Fourier transform, and in particular discrete time Fourier transform, which is the most general form of the Fourier transform that applies to discrete sampled signals. And so, the nice thing about the payoff of using the Fourier transform in systems is that now our system, which did this slightly novel operation of convolution in the time domain, in the frequency domain, that same expression just becomes multiplication. That if we have a system which we represent by the Fourier transform of its impulse response, h of e to the j omega, and we have a signal represented in the Fourier domain, x of e to the j omega, then the output of that, again represented in the Fourier domain, is simply the product of those two. At every frequency, we multiply the amplitude of that frequency and the input by the amplitude and phase modified by the amplitude and phase of the system frequency response at the corresponding frequency. And so here's this picture that we had from the moving average filter, where we had a magnitude response and a phase response. We put in two frequencies, and the output of the system was those same two frequencies, but with their magnitudes, now their relative magnitude was scaled, and their phases were shifted slightly. So that's, a very succinct way of understanding what a system is going to do to a signal. And we can go from the impulse response to the DTFT by taking the forward DTFT. X v to j omega is sum over all n of x of n e to the minus j omega. So you take the inner product of the entire signal with these complex conjugate sinusoids, and that basically picks out the amplitude of that particular sinusoid in the signal. And we can go back from the DTFT to an impulse response by taking the inverse of this transformation, which is basically taking the integral from minus pi to pi of x of e to the j omega, e to the j omega n. So we take each of these sinusoids, we scale it by the system magnitude and phase, we sum them all up, scale by 2 pi, just to keep everything scaled. We get the time domain back, the impulse response or the signal, whichever. So that's a nice, we can easily transfer between either of these two without difficulty. Once we understood the DTFT, we then generalized it to the Z transform, which is there's this very simple relationship between them, that the DTFT is simply x of z for z equal e to the j omega. So it really is just a generalization. If we have DTFT expressed in terms of e to the j omega, we can just replace each e to the j omega with a z, and we get the Z transform. But generally, we won't have, we might have, y of e to the j omega in terms of cosine omega on 2, right, which is what we have here, or something like that. And so it's not straightforward to transfer it into the Z domain, so that's why I put a shaded gray here. But we can always go back from the Z transform to the DTFT simply by expressing that we're only looking for the value Z transform for the values of Z, where Z equal e to the j omega. Yeah.
You said it's not trivial, but is there always for any DTFT, is there always a unique Z transform?
That's an interesting question. Does the DTFT uniquely specify the Z transform? I guess in general, no, because you're saying, well, there's some function that has this surface in the Z domain, and if I constrain the values on this single contour, is there any one surface I can have? And well, it's sort of that seems a little bit of a stretch, right? Because you can't. How can you constrain a whole surface of points by just a one-dimensional thing? But if you put a few assumptions onto it, then it does become true. So if you say, oh, and I want that surface in the Z domain to be the result of a rational polynomial in Z, then that's enough of a constraint. And so there is actually a procedure for going from the magnitude response to the actual to a finite order pole zero system using the Hilbert transform. It's kind of it's this amazing trick, but you can take just magnitude response, and that alone specifies it'll either match exactly one particular pole zero system or it won't. But if it does, then you can figure that out by this procedure. So again, because we're typically only talking about finite order constant coefficient systems, it turns out that it is unique. Not unique. We'll see that it's limited. We'll see some examples where we have systems with the same magnitude response but different phase responses, because you can do this thing of flipping roots, flipping zeros inside outside the inner circle. They have the same impact, but that's so there are a small number of alternatives which are equivalent. We'll see. It's not that with poles. It would be saying poles inside or outside would be causal or anti-causal. For zeros, it's okay to have zeros outside the inner circle, so they can still be causal systems, but they're non-minimum phase. We'll see what that means next week. But the nice thing about the Z transform is it gives us this perspective of thinking about systems, Fourier transforms, in terms of these roots on the Z plane. So we express the Z transform in terms of this rational polynomial in Z. So here now the output of the system is now this expression, h of z expressed as a rational polynomial times x of z. And h of z has these factors on the numerator, where the points where the h of z goes to 0, has these factors on the denominator, the points where h of z goes to infinity, goes to 1 divided by 0. And we can place these on the z-plane, and we've got all this stuff, this idea of the rubber sheet, where the poles are points where it's sort of pulled up to infinity, and zeros are points where it's pinned down to the 0 plane, or this idea of the magnitude or the response of the h of e to the j omega, the response of the system at a particular frequency, is just the product of these vectors from some point in the unit circle to each of the zeros divided by the product of the vectors from the point of the circle to each of the poles. And that can quickly help us understand that when we get close to a pole, we see a peak in the magnitude response. When we get close to the 0, we see a dip in the magnitude response. The Z transform, we motivated it by coming from the Fourier transform, but we have this thing which gives us the transformation directly from the time domain, again, simply by substituting into the DTFT. So we have x of z as the sum of x of n, z to the minus n. To go back from the Z transform to the time domain, we can also do that. That was the inverse Z transform. But again, it wasn't the most direct of approaches. Basically, we take our Z transform and rearrange it until we get terms that resemble this 1 over 1 minus lambda z to the minus 1, which we know from experience, if you like, is the Z transform of a lambda to the n, a right-sided windowed lambda to the n. But because of this property, because all these LCCDEs have impulse responses of this form, there's always an answer. And equivalently, you can say, well, if you think about the structure of this, you can always take a polynomial like this and express it as a sum of terms over individual roots or possibly pairs of roots. Finally, the link between the z-transform and the difference equation is neat and straightforward. We can take, because because a delay in time corresponds to modifying the z-transform by a z to the minus j or whatever, and because the z-transform is linear, then if we have something like this, a sum of weighted delayed terms in time, then the z-transform is...
Always in this section.
Okay. Let's hope it doesn't do that anymore. When I touch this screen, it sends click commands to the PC, which of course is not displaying on the screen anymore, so I'm just doing some random sequence of commands on that PC. If I don't touch it, it should be okay. No, okay, let's just see what it's doing. No, go away. What? Okay. That'll shut it up. It's straightforward to take an expression like this and just rewrite it as a z-transform. Just replacing the y of n's by y of z's, the x of n minus j's by z to the minus j, x of n, etc. And so then we can quickly get to the rational polynomial form of a particular difference equation. And in fact, I didn't write it this way, but we end up with a rational polynomial with the same p's and d's as the coefficients, and then these zetas and lambdas are simply the roots, the factors of the polynomial defined by the p's and the d's. So you see what I was trying to get to with this picture? I was trying to show how everything is kind of the same, and just we've got these different perspectives and they're all linked together. It ended up looking kind of crowded, but it was interesting to me to just try and lay them all out in the same thing. Any questions or observations about that? Anything I left off, you think?
Something I was wondering about before you showed us this picture.
Yeah.
Actually, the whole point of the z-transform was just to generalize the DTFT and make it easier to find it. Or that's what I thought before. But now looking at this, I see the z-transform just makes a clear connection between the LCCD and the DTFT.
Yes.
So
what is the point of z-transform? It gives us this link through here. So because I didn't draw any arrows from here to here, going from the difference equation to the DTFT.
But that is the whole purpose, right? To find the DTFT.
I hadn't thought about it like that before, but let's see. So if we just had an LCCDE and we wanted to know what the frequency response of that system was, one way we could do it is by calculating the impulse response and then calculating the Fourier transform of that. But that would be pretty painful because we'd end up with this infinite thing, and it's not at all clear how to calculate that. Of course, it would give us the right answer, and it's probably not that painful, right? But yeah, that seems kind of clumsy, particularly because we have to do this whole solving the LCCD thing, which never makes me feel good. So yeah, this is a much cleaner route, because here it's very obvious what's happening here. We're just rewriting the delays as some polynomial, and then this is very simple. We're just sampling that function on a particular circle. Yeah, that's a good observation. That's a nice point. Because for me, the point of the z-transform is very much that it explains the features of the Fourier transform. This is for me a very useful way of thinking about a system in terms of the gains, the way it modifies different frequencies. Obviously, if you talking about high pass and low pass, that's all about the gains at different frequencies. And then, but rather than having to just have a look at these curves and then be, well, I just solved it and it turned out to be whatever it was. It's no, they emerge naturally from these singular points on z-plane, and that seems like a much simpler way to understand what's going on. Yeah. Does this diagram Makes sense? Do you see what's going on here? Okay. Yeah, like I say, it's new. I'm wondering if I should introduce it earlier, but I guess it's probably best to introduce it now because it's a little bit confusing if you haven't already seen all the individual pieces. Okay. What would you like to do now? I could answer questions, or we could look at the example midterms on the website. A couple of people asked me questions about that. So I guess there are two. Also, any questions, or do you want to just have a go at that? Okay. There are two example midterms here. Somebody said last week that I think a couple people observed that one of them was much easier than the other. That the 2010 one was easier than the 2011 one. Is that right? Okay. I was not aware of that. I mean, so here in 2010 you get a difference equation and you have to analyze it through to the system and then figure out where the poles and zeros are to draw the pole zero diagram, and then figure out the output for a particular input. And the point of this, can I make this bigger? Yeah. The point of this is, well, this signal here, this input, is just the sum of sum of three complex exponentials, e to the j 0n, and then cosine is a half of e to the j omega 0n plus e to the minus j omega 0n. And so to figure out the output, you can take those three sinusoids, scale each of them by h of e to the j omega for those three values of omega, minus omega 0, 0, and plus omega 0, scale their gains and phases, and then add them back up again to get the output. It's going to be, again, it's constrained to only have a constant part and a cosine omega 0 part, although it's possible that one of those gets reduced to 0. I'm not sure. Then I do this thing where we say, okay, let's think of a new system where g of z is h of j of z, which is kind of an odd thing to do. But basically, if you have h of z written down, you then replace every z in the h of z with a jz, and you get a new polynomial in z, right? Because the z terms become jz, and the z squared terms become minus z squared. Yeah.
I don't have a question about this.
Yeah.
If you do C, you need the phase and the magnitude. You can read that out of a plot from B, for example.
Yeah.
But that's not 100% exact.
Well, it wouldn't be in general. Although, I'm not. I am not too.
I haven't done it yet, so
Okay. I'm not too fussy about that. My policy would be, there are maybe two ways to solve a problem. One is like to just do the math and get the exact solution,
So that's what I would
and which is normally what I would want you to do. Another way you could imagine doing it is you have a plot, you read off some values, and you scale them, and you get an approximate answer.
Okay, so I just write numbers in the plot, like the phases, so that you can see which are what they are.
Yeah. So that would give you an inexact answer in general, but I kind of like that approach because it shows that, well, you understand what's going on, and you've got the general idea, and so I probably wouldn't get full marks if you didn't get the exact answer, but it would get most of the marks. Okay. Because the last thing, it's very hard setting exams, right? Because what I'm really interested in is, as I said, the intuition of what's going on with signals and systems. But at the same time, I have to ask questions that kind of differentiate, right? That some people do better than others, because that's a good question. Because why? But that is kind of the point of grading, that we judge people, we score people. And so having math in there is a very nice way to say, well, you did this right or you didn't do this right. But my ideal is not that oh, your grade on DSP reflects how good you are at algebra, right? That's not the point here. The point is the grade on DSP is supposed to show how well you understand how signals and systems work. And so, you know, I'm not about just casting, you know, setting up some problem which is just an algebra problem and then just seeing if you can figure it out. The algebra part is not meant to be the part that tricks you out. It's the setting up of the problem that's meant to be interesting. So in this case, I forget exactly what it was, but the point is that the actual values of h of the j omega at these frequencies, the frequencies are very simple, right? Because if you look at the question, the actual frequency is pi on 2. So it's like, you know, four samples per cycle. And the system itself is like this. Is that right? So there's a lot of symmetry in here. So we're trying to evaluate at these points. So it's pretty simple to come up with the values for these points. Although it's in this case, the easy thing is just to plug the values of j omega in here, rather than to start measuring lengths of vectors in here, which will give you the same answer, but it involves rather more trigonometry than you would need. Right. So if we're trying to figure out the value at this point, which is z equal to j, we can just plug it in here and we get 1 plus 0.5 divided by 1 minus 0.5, which gives us the value of 3, the gain at that frequency. A point about these solutions and the style of the questions in general. You know, based on what I just said, when I'm designing these questions, what I'm trying to do is come up with a question where if you have the right insight, it's kind of simple to solve. Normally there will be a sort of a literal, a more sort of obvious way of doing it, which involves quite a lot of work, and then a kind of insightful way of doing it, which cuts out most of the work. So sort of understanding that, oh, well, in general, finding h of the j omega is kind of messy, but because I'm asking for it for this particular frequency, that makes it much simpler. That's the kind of thing that will happen, and I'm hoping that you spot to help you get through the question more quickly. And so if you look at a problem and it seems like, golly, that's going to be a lot of calculation and algebra for me to work it out, it's worth taking a minute or two just to see if you can think of a different way of doing it. I can't make it all trivial. I would if I could, but I'm not skillful enough at writing questions to make them all completely trivial when you spot the right way of doing it. But that is kind of what I'm aiming for. So there's this part where g of z is h of z with jz replacing z, right? So we have the h of z up here, but then when we replace that with jz, because this h of z only involves z squared terms, all that happens is that these signs flip. We end up with a different system, but interestingly, we end up with the system where the numerator and denominator are interchanged. This is not... We didn't, which we notice is the inverse system, right? So what we end up with is a system where the numerator and denominator are interchanged, which means that we have poles where we had zeros before, we have zeros where we have poles before, which, by the way, is the inverse system, or at least the inverse system up to a gain, because when we multiply those two systems together, the poles and zeros will all cancel out, so we'll get a system with no poles and zeros. But what actually happened, we said that g of z was h of jz, and so what we actually did was we took the entire z-plane and we multiplied it by z, which is rotating it by 90 degrees. And so what actually happened was when we rotate this by 90 degrees, then these zeros land up where these poles were, and these poles land up where these zeros were. Okay, so that was kind of the insight there, that it's this way of thinking about modifications to h of z as modifications to the entire z-plane, and how that gives you a system. It wasn't necessary to spot that. You could just do it mathematically, but that's kind of this nice way of figuring out what's happening here. And then it asks you for g of z here. The region of convergence, of course, is for a causal system is the region outside the radius of the largest pole. So for alpha is 0.5, right? So these two values are actually not in the region of convergence. This is well inside it, well inside the region of non-convergence, divergence, and this is on the edge. So we can't, these two values you should say cannot compute, not within region of convergence. These two values you can actually just compute it just by substituting it. Again, that was just a trick, because you can just plug it into the g of z and get a value out, but it's not technically the z transform because it's not in the region of convergence. And then this is just sketching it, which is just taking the system and rotating it. I don't know what I said about that. In general, for sketching a graph like this, so I cheated in the solutions and just got MATLAB to plot it for me. But what you would have to do in an exam is actually sketch it. So the things we're looking for when in a sketch like this is, so this is, there's a pole on the real axis, then there's a 0 on the imaginary axis, there's a pole on the real axis at pi. So we're looking for, qualitatively, a sketch that has maxima, where there are poles in effect, and minima where there are zeros in effect. And then quantitatively, we typically want to know the values at the extrema. So this 3, this 0.5, and the frequencies that the extrema occur at. In some cases where you've got poles and zeros interacting, you may not be able to get these values exactly, right? You could get them exactly, but it would be a lot more work. But then just saying the easy thing, approximately, the thing that will allow you to make it a good sketch, saying, well, I don't know exactly where the minimum frequency is, but it's going to be around this frequency, and at this frequency the gain is going to be this. So it looks something like this. That's good enough for a sketch. When you do that stuff, explain each of the things you've done. I want you to put them on the plot, but I also want you to say which parts of the plot are specifically placed and which parts are just drawing in between them, just so we understand the reasoning that's gone into the sketch, because that's very often the part that we're most interested in. So the second part was, second question was a DFT question. DFT didn't appear on my big overview plot. DFT was something we introduced when we were talking about the Fourier transform as the discrete version in frequency as well. It's sort of, and it's important because it's the thing we can calculate with computers, but we sort of dropped it for the time being while we're still talking about the Z transform and stuff like this. But it will come back later when we actually try and implement these things. The main things about the DFT that we know about at this point are it's not, it has these limitations in terms of its equivalent to the DTFT, which is that it's like the DTFT if the time axis was circular, right? So it's does everything right except the time axis wraps around and is of finite length. And so we can use it for convolution. We have to make sure the circular time axis is long enough to include all the points in our convolution without time aliasing, without wrapping back on itself. And if it isn't long enough, if you end up trying to calculate DFT as something which won't fit in the length of the number of points that you've got, then you do end up with this time aliasing. But you can predict what that's going to be simply by applying time aliasing to the full length version. So this is very much exactly what we were trying to do. That we're trying to do a convolution of some sequences using just DFT. And so because there are 12-point sequence and 5-point sequence, the convolution is going to be 12 plus 5 minus 1, or 16 points, 16 non-zero points. And so to do that with a DFT, we'd have to pad both of these out to 16 points, take the with zeros, take the DFTs, multiply them together, and do the IDFT. So that's the picture here. And then the rest of it is just what happens if we didn't do that. I guess the second part is just giving you a literal convolution. We could do this by padding these out and taking the DFTs and taking the IDFTs, which would be incredibly painful. Calculating a 16-point DFT by hand is not something you want to do. But we've just designed the system so it's linear convolution. So you just do the linear convolution, which in this case is very simple because it's just these two non-zero points. So you just take this signal, delay it by 4 points, and subtract it from itself to get the answer. But here, it's saying, well, if you didn't do it right and you did it with 8-point DFTs, so you got time aliasing, what would the answer be? And of course, because this thing is just, well, if this were IDFT, this would just be an 8-point convolution. I couldn't stop myself, I guess. I wanted this to be IDFT, but then I thought that's too easy, so I put DFT in. Assuming it was IDFT, it would just be the 8-point time alias version of this. So we just take the result from this part and fold it down so that the second 8 points get added to the first 8 points. But then here it's like, oh, it's DFT, not IDFT. But we know that the DFT and the IDFT are almost the same except for a conjugation and a scaling by n. So you calculate the IDFT, and then you say what the DFT would be by undoing those two things. I don't know if the conjugation actually does it. The conjugation becomes time reversal in the time domain. So that was just, being a bit tricky. Any questions about that? Okay. So the last year's midterm, I thought this was kind of straightforward. And I thought it was kind of neat as well. So I have these three, don't touch the screen. I have these three conjugate root locations. And then I just say, well, we've got a system. It's got a root at one of these three pairs of locations, but it might be a polar, it might be a zero. So that gives us 6 possibilities here. And how do those systems differ? And when we have just zeros out here, we have dips in the frequency response. And then as we go from A to B, the frequency where the dip occurs becomes a little higher. And the depth of the dip becomes a little deeper because at B it's closer to the inner circle than it is at A. And at C, it's also, actually it turns out that it's still just a dip and it's about the same, the dip is maybe the same depth as it was at B, but a little higher in frequency. So I only asked for the magnitude response. So the phase responses are going to be kind of different depending on whether the zero is inside or outside the inner circle, but we're not asked to deal with that. So that's not too bad. And these are, I guess you can read the exact values off here, but they're just sketches, right? You don't need to calculate anything at any great depth. I mean, to get the actual values of the minima here, if they're zeros, you do have to worry about the influence of this zero over here that has this gain that is maximal over here. But we sort of went through the effect of a single zero in class, and so that's all I was asking for, just putting very rough sketching of a couple of those things and putting them together. For the poles, it's basically 1 over the zeros, right? Once you've calculated for the zeros, you just take the reciprocal of that, you get the response for the poles. Except for the case of C, where we've got a pole outside the inner circle, so we've got an unstable system, so that was just a little trick to make sure that you were awake and pick that up. Yeah?
You don't say anything about the region of convergence in the question. How do we know part 6 that it shouldn't converge there? You say
Yes, I didn't say anything about the region of convergence. I didn't say it was causal.
in the answer, yeah, you say 6, you can't modify.
Yeah. Well, so that was a mistake, right, on my part on setting the question. I should have been more specific. But the interesting thing about, and it wouldn't be the first time that I'd put a mistake into a question sheet, but the idea about the test is that it's not, everyone has to deal with the same thing, right? And I'm just trying to judge how well you understand the material based on how you deal with it. So in that case, you could, if you were, I don't know how it looks to you, but because I know what I was thinking, it's obvious to me that that's kind of what I'm getting at. It's like, aha, are they going to spot this one's outside the unit circle? Certainly, you would want to say, in plotting C, in plotting C, if you say, well, this pole is outside the unit circle, so I'm going to assume that these are all referring to causal systems and this one's unstable, I'm not going to do anything. That's full marks. If you then say, well, this is a system where the pole is outside the unit circle, therefore it must correspond to an anti-causal system, and here is its magnitude response, which is just one over the other one. It involves a little more work because you have to draw the curve, but that would get you full marks or possibly bonus marks depending on how it was going. That would be the very clever answer. Yeah, we'll see. Yeah, right. So if you I will try very hard to make sure there aren't any ambiguities like that in the question. And so I'm not going to leave them in as this kind of bait for people who want to get extra marks. But if you do spot them, then that's the way to deal with it. I mean, we can try and deal with it at the time. If you can ask questions during the test, but mostly, in many cases, it won't be possible to fix it on the fly. So just explain what you're thinking, because that's like I say, what we really want to know is, do you understand what's going on? And so the more explanatory and discursive you are about that, the more we get an idea of exactly what you understood and what you didn't understand, and that's okay. We want to credit you for the understanding that you have. Which system has the impulse response with the lowest total energy? Find the values of that impulse response for n equals 0 to 4, approximately. The total energy, what did I say about this? I don't know. The total energy is like the integral I'm thinking about, the Parseval's relation here, that the sum of x of n squared is equal to the sum of magnitude of x of e to the j omega squared. And so we've just sketched these frequency responses. We're looking for the one with the lowest total area under the curve, which may or may not be, hang on, where am I? Wrong one. Yikes. Did this part freak people out in the solution? This is just saying if we have a single zero here, how do we approximate? Well, all I want to say is I want the response to be this length here, but then it's like, oh man, I have to worry about the opposite zero as well, so I have to worry about this length here. And it wasn't as beautiful as I'd imagined when I first set the question, but it's doable. We get something that looks roughly like that, and then we get these three different, that's superimposing the two zeros. Yeah. Okay. So here are the three responses for the zeros, and here are the responses for the two poles. So the peak gains here are about 5, and we're looking for the answer with the we're looking for the one with the smallest energy response, so we're looking for the one with the least area, which has got to be this one, right? C. Is that the answer? Poles at A. No, it's wrong. Okay, poles at A. So it's really? So this one's close to 1. Oh yeah, because these have got these huge chunks out here where they have high gain at high frequency. So this one, when you just look at it, it's like, okay, this one is the one that has the smallest area underneath, because it's, it doesn't have any of these big areas under here. So that's the answer, and then we calculate the impulse response. I don't know how I did that, but you've got the actual, for a few points, you've got the actual difference function. So rather than solving the whole LCCDE and finding the closed form and just substituting in, you can just run the machine forward for a few steps from the initial conditions to get those results. Yeah.
In the last question,
Yeah.
just assume there are two poles, there are two zeros when when you went to the solution. Yeah, when you get the
You want from here, or you want to see the solution?
when you get the values of the impulse response,
Yeah.
you use the long division.
Uh-huh.
Yeah, and you assume that there is two 0 points. Yeah. Because you see the HC equals that equation. Yeah.
Yeah.
This one, there is two, also there is two 0 points.
You mean, so you're saying for this version of HC we have zeros at these 2 points, but then if we actually multiply it through to make it a polynomial in Z, it would have Z squared on top as well, and it would be Z minus zeta, Z minus zeta, Z, I don't know why I use zeta there, Z minus something conjugate, and then GZ squared on top. Is that what you're saying? So there would be two zeros at Z equals 0?
Yeah.
Yeah. And so the effect of this, so there could be, by looking at the pole zero diagram, there are no zeros marked at 0, right? So you're thinking, well, that's not the, if you'd wanted that particular form, you would have had two zeros at 0 to indicate those two things. So this thing is actually Z to the minus 2 times that system. If you calculate the impulse response of that, it's just this impulse response shifted by 2 samples, right? That's what the Z to the minus 2.
So then alpha is different. If I don't
Oh, alpha is different.
I have to see those in front of that sequence.
So as I've mentioned, I don't plot the zero. I don't worry about roots at 0. And so this is definitely the this is what I'm thinking about. But you're saying that we've got h of z, and it's something on some roots, right? 1 minus lambda I z to the minus 1. But I can put some z's up here, and it, will change. You're saying it changes the impulse response solution. But you see, now what I'm thinking is this system corresponds to something that looks like here with some delays coming back and some feedbacks, right? And then a z to the minus 2 would be like a delay in here, right? Delaying the whole thing by some amount, possibly forward or backward. And certainly if it's a positive delay, then a positive delay, z to the minus 2, then the impulse response is pretty straightforward. So this is how I'm trying to make sense of what you're doing. It's like, okay, well, this corresponds to some kind of system. I've got a z transform, it corresponds to a system. And if I really want to know what the system does, I can always go back to thinking about, okay, there was some system with a block diagram. What would that have done? If we'd had a z to the minus 2 in here, it would have just taken the same impulse response, but been 2 samples later. If we had a z to the plus 2 in here, now we've got a bit of a problem, because z to the plus 2 is a non-causal system, right? A system that gives you the output 2 samples before it appears at the input. If I just want to close my eyes and not worry about it, I just take the impulse response and shift it back 2 points earlier. Sort of seems okay. In terms of an actual solution with initial conditions and stuff, I don't know. I'm outside the realm of how I can relate it directly to what makes sense. In terms of giving you advice for what to do with those kinds of problems in an exam, obviously the best thing is if you can read my mind and figure out what I was the simple thing that I was trying to do. That seems like a lot to ask, and it seems like a fairly risky procedure. But we'll try and. But if you explain what you're thinking, you're saying, well, here's why. So in your case, it's like you're looking at this, and it's like, wait, what happened to the two zeros? Right? You're trying to find the solution. If you say, look, I think you forgot these two zeros, but I'm going to assume that you wanted me to ignore them, and I'm going to carry on, that would have been fine. That would have actually been the right answer. If you'd not said anything about it and just ignored them, that would have been the right answer. If you say, I'm going to ignore them, then that's even better. Now, the worst case thing is, like you say, well, here's the problem you've specified, as best I can tell. I'm going to try and solve it, and you end up with this nasty thing that you don't know how to handle, right, with the system, which is a non-causal system. So I'm trying to what's my advice? If you find yourself in that kind of situation where it's like, there should be an intuition where you say, probably you didn't want me to solve this because I've got no idea how to solve this, or this doesn't make sense to me. Then say so, right? Just explain where you've gotten to, why you're having a problem with it, and we'll take it from there. Okay? Yeah.
Maybe more generally, I was just wondering, you're assuming that G here is a constant, right? There could be, just in general, more zeros or poles.
Well, we're starting from the pole zero diagram, so so we know that those are the only. The G has to be.
Oh, those are the only ones.
Yeah.
Okay.
Right. That if G was some general polynomial, then the pole zero diagram would have had more poles and zeros on it.
Okay.
Right. I mean, which is which is why it perhaps should have had zeros at 0. Okay. Any other questions? All right. Good luck, and see you again.